Hello students, and welcome back to Chemistry A. I'm Ms. Slate, and today we're going to be talking about hybridization, multiple bonds, and polyatomic dot structures. First off, let's look at the dot structures for the following elements: beryllium, boron, and carbon. So beryllium, 2 valence electrons, boron has 3, carbon has 4, and silicon has 5. So this is traditionally how we would draw the dot structures for these elements. However, we've observed that beryllium, boron, and carbon and silicon can form the following compounds. So as you can see, beryllium bonds with just 2 hydrogens, boron only bonds with 3, carbon and silicon both bond with 4, even though they're paired up electrons you would think wouldn't need to be shared like that. So the patterns in which these bonds are very unusual. It doesn't match what we would typically predict based on their dot structure. And that's because all 4 of these elements have undergone hybridization of their s and p orbitals. Hybridization is when you combine s and p orbitals for certain elements. So what happens is that an s electron gets promoted to the next highest energy p orbital. And so the highest energy s and p orbitals combine to form 4 equal energy hybrid orbitals. And we'll take a look at what that looks like for these 4 elements. First off, beryllium has an sp hybrid orbital. So instead of an s and then a p, there's just one sp orbital, and its 2 valence electrons get to spread out. Boron, likewise, all 3 of its valence electrons spread out in the sp2 hybrid orbital. Carbon and silicon both have all 4 of their valence electrons spread out in an sp3 hybrid orbital. And this matches what we see in the pattern of bonding for these elements. Now, one thing to remember is you are going to need to know that these 4 elements have hybrid orbitals. It's going to show up on the test, and it's going to show up on the exam. So this is something that you're going to want to know. So if we take into account that these 4 elements have hybrid orbitals, this is what their dot structures actually look like. Beryllium, its 2 electrons are spread apart in separate orbitals. Boron, all 3 in separate orbitals. Carbon and silicon, all 4 of them are in separate equal energy orbitals. And knowing this will make drawing the dot structures for their compounds much easier. One thing to also remember, though, is that beryllium and boron are both exceptions to the octet rule. When beryllium bonds, it's going to have a total of 4 electrons, and boron, after bonding, will have a total of 6. So these 2 elements are just fine with not having the usual 8. And that's another thing that you're going to have to remember, that these 2 are exceptions to the octet rule. So now let's do some practice with drawing some hybrid orbitals for carbon tetrachloride, oxygen gas, and nitrogen gas. Let's start by making the Lewis structure for carbon tetrachloride. So one good thing to help you keep track of everything is to make sure that you keep track of the total number of valence electrons that are going to be in your overall dot structure. So we're going to have 4 from carbon plus 7 from each of our 4 chlorine. And that's going to give us a total of 32 valence electrons overall. So we should have 32 dots in our finished dot structure. Well, I'm going to start with carbon, knowing that carbon has hybrid orbitals. So it's going to have its 4 valence electrons all spread out. Chlorine then can come and share one of these valence electrons. And we're just going to do this 3 more times. And this should be our finished Lewis dot structure for carbon tetrachloride. To double check to make sure we did it right, we should make sure all of our electrons, all of our atoms have 8 valence electrons. 8 around each of our chlorine and 8 around carbon. So that checks out. Now, let's look at the dot structure for oxygen. Well, each of our oxygens is going to have 6 valence electrons. So we should have 12 electrons total in our dot structure. So I'd start with my first oxygen. And my second one should be able to come in and share an electron. But if we do it like this, you'll notice that both oxygen atoms still have unpaired electrons. So they don't have 8 electrons between them. So what they're actually going to do is they're going to share 2 pairs of electrons. So our dot structure isn't going to look like this, but actually the dot structure will look like this. Now, if we count it up, each oxygen has 2, 4, 6, 8, 2, 4, 6, 8 valence electrons, just like they wanted. And in fact, when 2 pairs of electrons are being shared, we call this a double bond. Now let's take a look at nitrogen. Each of our nitrogen atoms is going to have 5 valence electrons times 2 for a total of 10 valence electrons. So let's start. Here's my first one. Now, again, we can see each of our nitrogens still have unpaired electrons here. So what they're going to do is they are also going to share multiple pairs of electrons. So if I draw our dot structure like this, now we can see that each of our nitrogens has 2, 4, 6, 8, 2, 4, 6, 8 electrons around it. Here we have our nitrogen sharing 3 pairs of electrons, so we call this a triple bond. So we just saw how oxygen and nitrogen share multiple pairs of electrons between each other. Again, 2 shared pairs of electrons is called a double bond. 3 shared pairs of electrons is called a triple bond. These can also be represented by lines in a structural formula for these molecules. Again, remember, multiple bonds are simply the result of having more than one shared pair of electrons between 2 atoms. Now, I'd like you guys to take a minute to pause the video and see if you can work out how to make the Lewis structures for carbon dioxide and carbon monoxide. I'll give you a hint, both of these are going to involve multiple bonds. Alrighty folks, let's see how you did. So carbon dioxide, we're going to have 4 valence electrons from carbon plus 6 from each of our oxygen for a total of 16 valence electrons overall. So I'm going to start with my carbon because it has hybrid orbitals, so I spread them all out. Then I'll bring in both of my oxygens. If we do it this way, though, with just single bonds, you can see that this doesn't satisfy the octet rule. So we're going to need to do multiple bonds. So I have 1 unpaired electron on each of my oxygen and 2 on carbon. So I'm going to need to share 2 sets of electrons between carbon and both oxygens. And so this is what your accurate Lewis dot structure should look like. The structural formula for carbon dioxide would look like so. Now let's look at carbon monoxide. Carbon monoxide, again, we're going to have 4 electrons from carbon and 6 from oxygen for a total of 10 valence electrons here. Now I should know right away that this is going to involve multiple bonds. So maybe the first thing I'll try is I'll try a double bond and see what that looks like. So when I do this, though, I can still see that I have 2 sets of unshared electrons. So carbon and oxygen are actually going to need to share 3 sets, 3 pairs of electrons. So this is what your accurate Lewis structure for carbon monoxide should look like. Its structural formula would look like this.